So the goal of section 4.6 is to kind of marry together what we've been learning about calculus with what we can do with technology. And personally, I like this marriage because I don't think we should pretend that you're on a desert island and have to do this stuff by hand and have no access to technology. So it's just not realistic. Let's start by looking at the graph of 4 sine of x plus cotangent of x in the interval negative pi to pi. So that's here, and it's kind of this interesting graph. You got these little dimples here and here, here and here. So, all right. You can pretty this up a little bit if you wanted to. If you click the tool icon in the upper right-hand corner, you can make your step size for the x-axis equal to pi. And that might make it a little bit more readable. So, and then maybe I'll zoom in a little bit on the x-axis, just so I can see things a little bit clearer. Now, typically speaking, what you have to do to figure out things about a function is look at its derivative. At least that's our MO in a calculus class. Tell you what, you do the first one, I'll do the second one. What's the derivative of the sine function?
Cosine.
Cosine. And the derivative of the cotangent is minus cosecant squared of x. And again, we're just going to focus on the interval negative pi to pi. Now, what do I want to do with the derivative? What is the derivative going to help me decide? Well, for instance, when the derivative is positive, what's it going to tell me?
Function's increasing.
Function's increasing. So let's do ourselves a favor. Let's shut off the graph of the function. So you can click this folder icon in the upper left-hand corner and just turn on the graph of the derivative. Now, one thing that's wonderful about Desmos is you can just click it and it gives you these points. And these points are gold. Why? Because these points are places where the derivative changes sign, correct? So one of the things you'll see is that the derivative is not defined at one point on this graph. Where is the derivative not defined? Can anyone tell?
0.
At 0, yeah. You've got a vertical asymptote at 0, and that's because cotangent is not defined at 0. Good. But other than that, we can do ourselves a nice little table of places where the function is increasing, decreasing, etc. You can get all the information you want just right here. So let me draw ourselves the graph that you're used to from sections 4.3 and 4.5. So x, f, f prime. Let me copy down a few numbers here, like negative 1.298, negative 0.578, and then the reflections of these 0.578 and 1.298. So there's my little table. So why did I choose these points? These are the points where the graph crosses the x-axis. So these points are critical points. They're either going to be minimums or maximums, relative mins, relative maxes, those kind of things. And the derivative was 0 at all of these points. I probably should put in a column for 0, but the derivative didn't change signs around there either, so I'm not going to worry about it so much. All right, to the left of negative 1.298, what's the sign of the derivative? What sign should I put here based on my graph?
Positive.
To the left of it, the graph is below the x-axis.
Oh, right. Negative. My bad.
It'll be negative. And then to the right of it, that's where it's positive. So it's going to be positive, and then negative. And then you cross over the asymptote. Generally, I probably should have a 0 there, but it doesn't change sign. And then what? Then positive and the negative again. So that's telling me a lot about my function. Other way around. Sorry. I started off in the wrong pattern. So the function's decreasing, then increasing, decreasing, increasing, decreasing. Wow, that's a lot of nice information that you get pretty easily from this. What's it saying about this point right here at negative 1.298? Decreasing, then increasing. What haven't I heard from today?
It's a relative minimum.
Yeah, thanks, Chloe. It's a relative minimum. Relative min. And this is going to be a relative max. And this would be a relative min. And a relative max. Awesome. Let's see if that makes sense in terms of the graph. So we can turn back on the graph and take a look here. So right here, we said that we should have a relative min, and we do. Cool. And then a little ways over, right here, we said we have a relative max, and we do. And so on. Relative min, relative max. Perfect. It's exactly lining up like we should, or like we expect to see it. Again, I want to shut this off for a second because it just gets a little too busy. The derivative tells us everything we know or everything we need to know about the function in terms of where it's increasing and decreasing. Now, when you differentiate this, you get the second derivative. So derivative of cosine is negative sine. Let me take a second to mark on this notation here. So we've got minus cosecant squared there. So minus cosecant squared of x, which would be minus cosecant of x squared. Now, on the test, for problems like this, a few of you wrote minus cosecant of x squared like that. And you actually did the work right, so I didn't like take off any points or anything like that. But just so you know, without the parentheses there, you're really just squaring the x, which is a much different function than this. Just saying, just throwing that out there just as an FYI. Now, to differentiate this, you got to use the chain rule. So the 2 is going to come out front. I'll get negative 2 times cosine, or cosecant, I should say, cosecant of x to the first power, cosecant of x to the first power, which I'm not going to write the first power, times the derivative of the inside. And the derivative of the inside is another wonderful mess. It's going to be minus cosecant of x times the cotangent of x. The minuses come together, minus and minus, it's a plus. Cosecant and cosecant, I end up with minus, that's going to be a 2 cosecant squared of x times cotangent of x. Whew. So all that goes into my second derivative. Yay. And there's that term. If you wanted to see all of it, you could expand it. But there's our second derivative. Let me shut this off and let's just look at just the second derivative. And let's think about what kind of interesting things we need to see here. Well, we want to find out where the second derivative changes signs, correct? So changes here, it changes at 0 because you go from negative to positive, and that changes here. So let's do a little table there for the second derivative, kind of like what we did for the first derivative. This time we're only going to have 3 points instead of 4. That's fine. But I have to include 0, even though 0 is not part of the domain of the function. Function is not defined at 0, but the function can change signs in the first or second derivative at 0. I really should have included 0 on the last one. Well, I got 0 here. We need to include negative 0.58 and positive not 0.58, negative 0.858, 0.858 and positive 0.858. So here's my table. Let's see if we can organize some information around this. So I want to look to the left of negative 0.858. So to the left of negative 0.858, the second derivative has what sign? Is it positive or negative there?
Positive.
It's positive, and that's all we need, is that it's positive. Thank you. So it's positive there, and then it's 0 here, and then it's negative. Now, the function does not exist at 0, but it can change signs at 0. So we got to look on the other side of that vertical asymptote. And as we cross 0, 0, 0, comma 0, it's not really a point on the graph, but as you move from the left side of this to the right side, what happens to the sign of the second derivative? Second derivative between 0 and 0.858 becomes positive. So, okay. Positive here, 0 here, and then negative to the right of 0.858. Beautiful. So what does that tell us? Well, it tells us, again, some more stuff about our function. The function is concave up here, concave down, concave up, concave down. In particular, that tells me that this is an inflection point. And this is an inflection point. But 0, how come 0 is not an inflection point?
Doesn't exist.
Yeah, it doesn't exist on the graph. It's just not a point on the graph. So as far as inflection points, we should see them here and here. Let's take a look at our function now. So changes concavity, yeah, about right there. And of course, the graph has moved a little bit, but about right here is where it changes from being concave up to concave down. Tough to see, tough to spot without calculus. And then it's concave down, then concave up until we get to wherever this point is, about 0.858 over here. And then it switches from being concave up to concave down. So you're using calculus, but you're also using technology. And I kind of like the marriage of the two. So, all right, there's our first example. How are we looking on that one?
Good.
Doing all right there? All right, let's try another one. I'm not sure we're going to get much beyond example B today or not. Okay, use a computer algebra system to graph f and define f prime and f double prime. Use graphs of the derivatives to find the following: the intervals where it's increasing, intervals where it's decreasing, maximum, inflection points, interval where the function is concave up and concave down. Basically, all the questions we've been answering all along by doing the calculus and doing the algebra. Now we're going to kind of back things off a little bit. So let's see. Let's go to our function. And let's just do it over here. I'm going to shut off my previous examples. And then let's go down to example B here. Oh. Should I have this, that one? Yeah, that one's defined. Okay. So there's example B. And we'll turn on the graph of the function. And boy, it's not showing up very good, is it? So let's do this. Hit the shift key and take your wheel and scroll and zoom in along the Y direction. And that's a little bit easier to see. Let's notice something about the domain first. This is example B. Can you tell me what the domain of this function is?
0 to infinity.
Yeah, 0 to infinity. Now it actually can equal 0 because you can take the square root of 0. So we're okay there. So AC is exactly right. It's 0 to infinity. Probably a good idea to look at that first, because you don't want to, end up with inflection points and mins and maxes that are outside that domain. Can do that in certain examples. I don't think it's likely to happen in a situation like this. All right. Now you can use Desmos to extents to find this, that, and the other, but let's shut off this graph and turn on the graph of the derivative. The graph of the derivative is not terribly interesting, but it does give me one important point, which is right here, 0.1208, which even to me doesn't look like a familiar number. So I'll do X, G, and G prime. So 1.208. And all I'm doing is I'm making a nice little table like this. The derivative crosses the x-axis here, so that's fine. And then what? Well, we need to know what's happening with the derivative to the left and to the right. What symbol should I put to the left and to the right? To the left of 1.28, what sign does the derivative have? Is the derivative positive or negative there?
Positive.
Positive, yeah. And all you're doing is looking to see if you're above the x-axis or below the x-axis. Don't get confused with saying, oh, well, the derivative is decreasing. No, 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 no. The derivative is positive, which means the function's increasing to the left of this point, and it's decreasing to the right of that point. We can see that when we look at our table, and we can also see it even better when we look at the graph of the function. Let's shut off this. It's increasing until we get to this point, about 1.208. and it's decreasing after that point. So perfect. Our first derivative makes nice sense out of what we're seeing here. So increasing, decreasing, that makes this a relative max, at least a relative max. And I think in this one, it actually turns out to be a global max, relative max. And by global max, it's the biggest Y value that you've got there. All right. How about the second derivative? Let's take a look at the second derivative. And even with, you know, some nice technology, it takes a little bit of finesse to see what's going on with the second derivative, because the second derivative hugs the x-axis so closely. So I'm going to zoom in some more on the x-axis and see that, oh, it does indeed cross the x-axis at this point, about 2.618. So x, g, and g double prime. So 2.618. Build our little tables here. Second derivative was 0 there. Well, what about to the left of 2.618? What was the function doing there? Was it positive or negative? Looks to me like this graph is below the x-axis. So it's negative and then positive. So it's concave down, then concave up. That tells me something special about this point. What does it tell me about that point?
Inflection point.
Perfect. Thank you, Sandy. It's an inflection point. Nice. And with these two charts, you can answer all these questions. The intervals where it's increasing, okay, well, that'd be 0 to 1.208, or maybe you have to round it to 2 decimals. Where it's decreasing, 1.208 to infinity. Perfect. Concave up, concave down, minimum, maximum, etc. Now, as far as the maximum is concerned on this, all you have to do is take your value for x, which was 1.208, plug it in there, and then you're going to get your maximum, all right, which is going to be close to 0.08 someplace. So it's nice. Once you've got these graphs down and understand what they're telling you, you can get all the information you need. The one thing that you're not going to get, I don't think, is if they ask you for an exact value. If they're asking you for something like square root of 3 as opposed to 1.732, all right, you're not going to be able to get that from Desmos or your graphing calculator. Just a real quick mention on your graphing calculator, finding these points is a little bit more challenging. Let me go back and look at our previous example. Let's see, clear this out. And let's just look at the first derivative. For our previous example, what was the first derivative? It was 4 cosine of x minus the cosecant squared, which is kind of a problem for you because you can't just type in cosecant squared here like you can in Desmos. You have to type in parentheses 1 divided by sine of x, and then hit the squared key. So that's your first derivative. If I graph that, say, between negative pi and pi, and on the y-axis, I'm just going to go between, say, negative 9 and 9. Hope that does it for me. There you go. So I got a reasonable graph But finding these points is a little bit more of a pain. To find these points on a graphing calculator, you're going to hit the second menu, then the calculate menu, and find the zeros. So you click 0, trace around till you find a point, or you can just type in a value if you want. But suppose I want to find where this is 0. It's going to ask you for a left bound, meaning you want to go to the left of wherever you think the 0 is. Now I'm going way past it, just so you can see that I'm to the left of this. You press enter to do the left bound, and then once you get to the right of your point, you press enter again. It says, okay, look for a route between these 2 points. And now your calculator is saying, okay, well, give me an initial guess. You know what? Just press enter again. It's the easiest thing. You do all that work just to find that 1 point. So it's here that you might want to notice that these things are symmetric. So that you really only have to look for 2 points as opposed to 4. But it's just not as user-friendly as, say, Desmos. Okay, but I would advise that for Calc 2 that you know how to do this on the graphing calculator rather than just rely on Desmos. I doubt you're going to be able to use Desmos on an exam in Calc 2. So, okay, are we looking all right there? Are you getting the idea with using the derivatives and technology? It can make your life a little bit easier. You just have to keep in mind what all these things are telling you in terms of mins, maxes, inflection points, concave up, concave down, etc. So, all right, we'll stop things here.